Hello students, today we're going to learn section 2.6, graphs of rational functions. Now the key to graphing a rational function is we have to identify the asymptotes. So graph asymptotes first. Asymptotes are like boundaries. Find the values to the left, middle, and right of vertical asymptotes. So these are the two key parts when graphing rational functions. Vertical asymptotes occur when a variable in the denominator causes the value in the denominator to equal 0. Horizontal asymptotes, you have to compare the highest degrees from numerator and denominator. So with a horizontal asymptote, if the highest degree in the numerator is less than the highest degree in the denominator, then the horizontal asymptote is at y equals 0. So again, when we're comparing numerator and denominator, we're talking about the highest degree. If the numerator degree and the denominator degree are equal to each other, then the horizontal asymptotes, it's going to be at y equals the ratio of the leading coefficient of the numerator over the leading coefficient of the denominator. And if the numerator degree is greater than the degree of the denominator, then the horizontal asymptote does not exist. What's going to happen is, depending on what the expression is in the numerator and denominator, you can have a diagonal linear asymptote. You can have a parabolic asymptote. You could even have a cubic asymptote. All right, so example 1. Let's graph f of x equals 2x squared minus 2 over x squared minus 4. So the first thing we're going to do is we're going to look for our vertical asymptote. Again, vertical asymptotes, it's just like finding restrictions on the domain. Set the denominator equal to 0, so x equals negative 2 and 2. So when we factor this is 2 times x squared minus 1 in the numerator, and in the denominator it's x plus 2 times the quantity x minus 2. So to find the vertical asymptote, you just set each factor equal to 0, so you have negative 2 and 2. Horizontal asymptote. Let's compare the numerator, the highest degree in the numerator, to the highest degree in the denominator. If you notice, they're the same. So that's what we mean by numerator equals denominator. So your horizontal asymptote is going to be the leading coefficient in the numerator over the leading coefficient in the denominator. So the leading coefficient is 2 in the numerator, the leading coefficient is 1 in the denominator. So your horizontal asymptote is at 2. So that's what we're going to do. We are going to draw the vertical asymptote. And again, what I said earlier was asymptotes act as a mirror. Asymptotes act as a barrier. So x equals 2, this is your first vertical asymptote. X equals negative 2. And your horizontal asymptote, it's y equals 2. So horizontal means you go left to right. So there's y equals 2. That's your horizontal asymptote. So now we found our boundaries. And after we find our asymptotes, I mentioned earlier, we look for values to the left, middle, and right of the vertical asymptotes. So now let's take a look at the left. So when I say left, look at your left asymptote. And now substitute values into our function. So to the left of -2 is -3, -4, and -5. So these values are to the left of -2. All right, so let's graph this. I'm sorry, let's find the value. So put parentheses. So put parentheses 2x squared minus 2, close parentheses, divided by parentheses x squared minus 4. So instead of putting this and doing this by hand, all you have to do is put these values in the calculator. So for example, put second trace, you're going to calculate a value, and you're going to find out what -3 is. So put -3, and you get 3.2. Second trace again, hit value, now put -4. And then you get 2.5. And that's what you're going to do with all these values that you're substituting back into the function. So again, put your function in the calculator and then hit second trace. All right, so we have -3, 3.2, -3, 3.2. So we're going to approximate right about here. This is -4, 2.5, -4, 2.5, so -4, 2.5, right about there, and -5, 2.3, so it's a little lower. So again, I mentioned that these asymptotes serve as a boundary. So as you're moving towards these asymptotes, it gets closer and closer to the boundary. So that's one part of this function. Now we have a middle part, meaning there are two vertical asymptotes, so we have a middle section. So now what you're going to do is find values between -2 and +2. Well, -1, 0, and 1. Again, all you do is hit second trace. You're going to calculate a value, and then you put -1, hit enter, and then you get your y value. So that's how I got all these values. So we're at -1, 0, 0, 1/2, and 1, 0. So it looks like a parabola for the middle part. And again, the reason why these asymptotes are important, it guides us to see how close we're getting to the asymptote. All right, and now we have a right part of this graph. So here's your most right vertical asymptote. So now let's test the values to the right. So we'll just put 3, 4, 5. So again, 3, 4, 5 is here. Put it in your calculator, and let's graph. 3.2 is roughly here. 4, 2.5 is roughly there. And 5, 2.3 is roughly there. So again, these asymptotes act as a boundary. So it guides you to how close you're going to get to the boundary. Okay, so this is our rational function. This is a function because it passes the vertical line test. If you drew a vertical line, it only touches the graph once. All right, so that's example 1. Example 2 is we have g of x. So g of x equals x minus 4 over x squared minus x minus 12. So let's factor the denominator. That's factorable. So now our vertical asymptotes are going to be at x equals 4 and x equals -3. Again, set each factor equal to 0, get x by itself. So x equals 4, x equals negative 3 are the two vertical asymptotes. Since the numerator, the degree in the numerator is 1 and the highest degree in the denominator is 2, the numerator is less than the denominator. Therefore, the horizontal asymptote is at y equals 0. And that was at the beginning of the notes. Alright, so let's graph. We're going to graph x equals 4 and x equals negative 3. So let me plot this here. Okay, so this is one vertical asymptote. Now, x equals 4 is a vertical asymptote, but it's what you call a removable discontinuity. It's a removable asymptote. The reason why it's removable is x minus 4 over x minus 4, that reduces. So now you're really left with 1 over x plus 3. Well, what we're going to do is we're going to find out whenever you have a removable discontinuity, what ends up happening is it becomes a whole. Okay? So here we just have one vertical asymptote. We have a right and a left. So let's just do the right side. Again, you can put this function in. I would put the original function in, not the simplified, because if you didn't factor and reduce this correctly, then you're going to get the wrong results. So put parentheses x minus 4 close parentheses divided by parentheses x squared minus x minus 12. All right, and then go second trace. You want to calculate a value. So now to the right of negative 3, I chose negative 2. I chose 0. I chose 4, and I chose 5. So what happens is when you substitute all these values in, you'll get 1 1/3 and 0.13. Now the reason why this is in red is because this is our whole. If you put 4 back in here, you're going to get undefined. It's not going to work because the point doesn't exist. If you put 4 here, you're going to get the removable discontinuity. We also call this a whole. Okay, so now this here, this becomes a whole. And it's also known as a removable discontinuity. All right, so when I substitute 4 back into the reduced function, that's 1 over 7. 1 over 7 is approximately 0.143. All right, so now let's plot these points. Negative 2, 1, 0, 1/3, 4, 0.143, and 5, 0.13. So again, these asymptotes acts as a boundary, and it just helps us guide what the graph is going to look like. So this is what you call a hole, because there's a hole in the graph. Now let me draw the horizontal asymptote, because that's what we should have done earlier. And you might not be able to see this because that was part of our XY axis. Okay. So here's our horizontal asymptote, our vertical asymptote. We graph what was on the right. Negative 2, negative 1. I chose 4 on purpose because I wanted to see where the hole was. And I chose 5. Next, values to the left of this vertical asymptote. Negative 4, negative 5, negative 6. So negative 4, negative 1. Okay. Negative 5, negative 1/2. and negative 6, negative 1/3. So you can see it's getting closer and closer to 0. Okay, so again, that's your rational function. That's a graph of the rational function. Again, find all your asymptotes, and then look to the right and left of each vertical asymptote. All right, so that's example 2. And example 3, we now have h of x equals x squared minus x minus 2 all over x minus 3. We're factoring, there's nothing we can reduce. So again, the vertical asymptote, look at the denominator. X equals 3 is your vertical asymptote. Horizontal asymptote, well, the degree in the numerator is greater than the degree in the denominator. Therefore, the horizontal asymptote does not exist. But what we are going to have is we're going to have a diagonal asymptote. It's also known as a slant asymptote. Okay, diagonal asymptote, slant asymptote. So it's just a linear equation. Therefore, it's a line. So to find out what your slant or diagonal asymptote is, you take this expression divided by this expression, just like what we did in the previous section where we did long division. This goes inside the division box, this goes outside the division box. 2 terms on the left outside, so we go 2 terms inside. So x times x is x squared, x times negative 3, negative 3x. Subtract, take the opposite signs. So we're left with 2x minus 2. 2 times x is 2x. 2 times negative 3 is negative 6. Change the signs, this is now 4. So we're going to look at this portion here, not the remainder. So this is going to get us our slant or diagonal asymptote. So first, let's graph the vertical asymptote at 3. So vertical asymptote at 3. Okay, so that's our vertical asymptote. And now we will graph our slant asymptote. Well, our slant asymptote, all it is a line. So if you remember how to graph a line, y equals mx plus b, this is your slant asymptote. Okay, again, that's called your slant. We can call it diagonal asymptote. So that's our slant asymptote. So you start off on the y-axis at 2. And if you remember how to graph lines, your slope is 1 over 1. So 2, rise 1, run 1, rise 1, run 1, rise 1, run 1. So this here, this is your what you call your slant asymptote. So again, what we're going to do is we're still going to find numbers based on the vertical asymptote. So we're going to have 2 parts, the left of this and the right of this. So let's look at the left. So the numbers I chose were to the left of 3. So I chose 2, 1, 0, -1, and -5, just to see what happens here. So when we found those values, again, based on the vertical asymptote, we get 2, 0, 1, 1, 0, 2/3, -1, 0, and -5 and -3.5. -1, -2, -3. So right about here. Look, that's pretty good. It's getting close to our boundary, our asymptote. So if you can see the dots, you're just going to connect them. So there's one part of the graph. Now based on the vertical asymptote, let's look at to the right of 3. So that's why I have the word right. So to the right of 3 is 4, 5, 6. So there is 4, 5, 6. Put in the calculator. So 410 is up here. 5, 9, 5, 9, and 6. It's starting to go back up, 6 and 9.3. Let me just extend this. Okay. So here is our other part. All right. So that is the graph of example 3. So this is h of x. So that's our graph. All right. So again, what you have to do is find your vertical asymptotes from the denominator. Plot the vertical asymptotes. Horizontal asymptotes, compare degree from the numerator and denominator and compare them. And you'll have 3 situations. Either y equals 0, y equals the coefficients of the numerator, the leading coefficients of the numerator and denominator, or you won't have a horizontal asymptote, but you will have a slant. You could have a parabolic asymptote, a cubic asymptote. And then from there, based on the vertical asymptote, check numbers on the left, check numbers on the right, and that's how we have this table. All right, that's it. Thank you. Have a good day.